No, well, we would say that this angle right here is a 90-degree angle. And then this one over here, like that angle is 120.
I missed it.
You did have your 90-degree chance.
No.
What, angle?
Is there another 90-degree angle? Like after this one?
After this.
Just sit tight and we'll see.
I think so.
What about TECL4? Can I have you try to do the dot structure of TECL4?
The TE in the middle.
T is in the oxygen family.
The C.
Oh, okay.
I know, it just doesn't feel right.
Oh yeah, you have
So we have the TE in the middle, and the 4 CLs around it, and it looks like that all is right in the chemistry world, until you count your electrons. You count them up, and there's 32. You look over here. Ah, I need 34. 2 electrons, and no, we don't. Double bonds will reduce the number of electrons in the structure. We need to add 2.
Half gone.
So
God, don't do it.
It doesn't look. I know. I don't want to.
Don't do it, Mr. Moon.
But I know that I can't put them on the CL, so
No.
there it is. I have to.
Why would you do such a thing?
I-
God.
Gosh, don't make me feel worse, Hassan.
I'm sorry.
All right, well, what shape would this make then? You see now that it's a coordination number of 5. We have the 4 atoms bonded plus that lone pair.
Ew.
So the coordination number of 5 has its base shape, the trigonal bipyramid, this thing. And with 1 lone pair, that means one of these electrons has to go off. It's got to go out. So which one would come off? Would one of the top or bottom ones, or would one of the waistline ones come out? How would we know? Well, we think, not we think, I do know, that one of the 3 atoms along the waistline is going to be the one that comes off. You can still maximize your space in between the atoms with this one coming off. So if we have this come off, we're now down to this, the TE with 4 CLs and the lone pair. Now what is the shape of this? I see the snowman. You got the head, body, and the bottom part for the snowman, and he's like he's doing this, giving you a hug, or getting ready for it. See it? The hugging snowman?
Why is arms the size of his head?
Like you
It's a
just.
snowman, Justin.
Disproportionate, Justin.
Especially you.
Scientists didn't think snowman. Maybe they lived in a warm climate. But what they did see was something else that kids would think of.
Oh, it's an ant with only 2 legs. Seesaw.
It's a seesaw, a teeter-totter.
Two-legged ant. It's a 2-legged ant.
Yeah, 2-legged
It's a
ant.
very sad ant.
This is the name that they've given this shape is a seesaw shape.
What?
It is, seriously. They think of this as a teeter-totter. In fact, I have that model. Look at that, there it is, the seesaw.
That's so sad.
You've got the 2 down coming at 120 degrees. Yeah, you can't get that 3-dimensional perspective very well, but it does have the 2 coming down. And the lone pair
No, it's no.
is up there, pushing down those, keeping them at the 120 degree angle.
No, definitely.
So yeah, as much as that doesn't seem like chemists would come up with that, that's what they call the shape, seesaw shape. And now the bond angle, what's the bond angle? See how this lone pair is up here? And it's kind of spreading out and pushing down on those. So is that still a 90-degree angle?
No.
Well, no, not anymore. Now, I will tell you, this one lone pair trying to push on 4 other electron pairs, it's not as effective anymore, and you're not going to get that full 2-degree squeeze. So the way that we describe the angle on this is we're going to say less than 90 and less than 120 degrees. So I don't know what the angles are, but I know it's less than 90 and less than 120.
Wait, so it could be like one.
What?
What are you asking, Justin?
It's like 100.
Wait, so it could potentially be like 1 degree.
Oh, 1 degree. Yes. Yes.
What if it's like 100? Because that's less than 90. 120 is more than 90.
I was talking
Well,
about-
no, we're talking about 2 different angles here.
Like compare
The angle from that to that is no longer a 90-degree angle because those are getting pushed in that way, away from the lone pair. So there's the 2 angles on there. Anybody have any other questions about that? So it gets a little bit complicated as you see as we get higher coordination numbers. The next one that we have, are you good doing dot structures? You feel very confident and comfortable doing these? Because they'll all start to look the same. I'll just do this one. ICL3 is going to look like this. We have an I with 3 CLs. And then all the CLs, of course, are going to have their lone pairs. But then with the iodine, you're going to find to get enough electrons, as weird as that's going to look, you put the 2 lone pairs on it, not just one.
No.
It's
It looks nasty like you
symmetrical.
here.
So
It almost starts to look symmetrical.
yeah, it's better than.
Now that's the dot structure. What does the actual model look like?
Yeah.
It's not so symmetrical looking. I guess it turns out to be more so than maybe you think. So we're going to take another atom off of here. It's still a coordination number of 5. You count up the atoms and lone pairs, there's 5. One of these other ones along the waistline is going to come out. So what do we have now?
Yeah, here's some.
Or a pregnant snowman,
Oh, good.
right? You got that going on too. And you can call it a pregnant
Bowling
snowman.
guy.
What?
Someone's like bowling.
A
Or
very-
bowling, yeah.
Bowling man.
I took only one.
Now, when scientists saw this one, they just did that. They saw, oh, it looks like the shape of a T. T-shape. T-bone.
Driving.
T-shape.
T-shape.
Yeah.
Yeah.
Wait, the thing is.
Nisha, that's a T.
Wait, but the thing
Fine.
is longer than the why is the horizontal part
Yeah,
longer
yeah, I
than-
know, I get it. And they do have the model for that one. That's a sideways T.
It's gonna be
Yep, but that's what they are going to call that one.
an L shape.
Okay, is the bond angle 90 degrees?
Yes. No.
No, because we have the 2 lone pairs there and there. We do put the squeeze that way and that way, so it's more like that.
Less.
It's just under 90, so it's less than 90 degrees.
Umbrella.
Yeah, it's gross in a little bit.
Yeah, it would be more of an umbrella shape. But you know, we have 2 lone pairs would be pretty good about pushing those in. Yeah, they still call it T-shape. Okay, moving along. This is called the triiodide ion.
Oh.
I3 with a -1 charge.
I.
Yep.
It's bigger.
So it's going to be I.
Okay, all
All good on the outside eyes, but the middle eye, Girish will like it, but nobody else will. Wait,
Cheers. Dude.
what?
You're disgusting.
He likes that.
So you see, this middle iodine doesn't have 2 lone pairs like you would normally see. It's got 3 lone pairs. In order to have the right number of electrons, it's got to have 3 lone pairs. So we still have a coordination number of 5. And we're now going to have to take another atom off of here. Well, we've already taken 2 out of the 3 on the waistline. Let's take that last one off. And what are we left with?
Linear.
Once again, we're back to linear in shape. Yep, that's a linear molecule. Here's a model of I3 -1. And noted, and they've shown the lone pairs on there, all of the lone pairs along the waistline. You got the top, middle, and bottom all lined up, 180 degrees. Uh-oh, I just lost. Maybe. Huh.
Why does sparkboard being so strong?
A shame. This is linear, and the bond angle is 180. 180. I've lost my spark board.
Wait, but
Wait, so with the two lone pairs on the top of the eye, it's like not, it wouldn't like push against it to make it smaller, like the angle, like because in the
Those
other-
two?
But they're
Yeah.
pushing-
Well, it's not really above.
they're all equally like-
Yeah, they're trying to draw it in
Oh,
three
it's like-
dimensions.
oh, it's like-
Yeah, they're coming straight out like that.
Oh, okay.
oh,
See that? So, yeah, they're pushing out, out, and out, so there's the same push there and there. Yep. Well, that's gotten us through the coordination number of 5. We have just 3 more shapes. You got 3 more shapes in you?
no, I got 0.
Well, we're going to do, oh gosh, I have no,
Wait, just use it.
I got no nothing. Oh, maybe I have something?
Wait,
Maybe
we should
I can't
recalibrate.
draw. Okay. Well, we can at least advance with this. The next one is coordination number of 6. That's where we get our friend SF6. I'm going to move our camera over so I can write on the board. So we saw yesterday what SF6 looks like. We had the S in the middle with 6 fluorines around it. I'm not going to put all of the lone pairs around the fluorines because I don't think we need that to know what the shape is. So around the S, we have 6 atoms bonded. And now, what is this thing going to look like? We're going to get a shape that looks like this. Kind of similar to what we saw with the trigonal bipyramid, but what do you see in the middle?
4.
There's 4 atoms, not just 3 atoms. So if I turn this a little bit, maybe 90 degrees, you get the same thing. It's a little more symmetrical, isn't it? So, okay, how are we going to name this thing? If you can imagine, remember how we did the tetrahedron where we just connected and make triangular faces? If I were to make triangle faces, how many faces would there be? 1, 2, 3, 4, and then 5, 6, 7, 8. Octahedron. Octahedron. What's the angle?
Oh, 90.
Every angle is 90 degrees.
Oh,
I was gonna say.
Where were you?
I'm not. Well, I wasn't
When the class is
So this thing is octahedral with the bond angle 90 degrees all the way around. And then moving on, 2 more. We're getting there. Now we're going to wind up taking one of these atoms off. In ICL5, I don't know if you can see. Can you see that marker? Like Annie, can you see that? What's written on the board? Can you? So if I have ICL5, the dot structure is going to wind up looking like this. You have an I, and then a CL, CL, and then we'll have a lone pair on that too. So we have 5 bonded atoms in a lone pair, coordination number of 6. One of these has to come off, so I'll just take one off. And yes, we now have, and I'll take that out too, we have a square pyramid. Now remember, when we did the trigonal pyramid, I said, hey, make sure you call that one a trigonal pyramid because if there's going to be another pyramid, this is it. This is a square pyramid. Notice the base has 4 corners to it.